Hi, everybody. Welcome to my kitchen. I'm broadcasting from here today because it's a little later in the evening and the boss is asleep. And if I wake her up by recording upstairs, then I'm never going to get to sleep. Anyway, today's topic is going to be the Fourier series. Now, we already started talking about this conceptually, and I used the phase parameterization there to kind of draw this picture of how we're going to reconstruct continuous functions by adding together a set of functions, a set of modes that come from solutions to the wave equation. Today, I'm going to go to the more traditional transcendental parameterization, where we'll build up how to actually find those coefficients, right? How to actually find the Fourier series, both from an analytic standpoint, and then I hope I'll also get to show you how you might be able to make some of these integrals a little bit simpler by using some numerical methods. Okay, so let's get to it. All right, so we do have quite a bit of work to do in tying all of these pieces of the Fourier series together. And eventually, in the next couple of minutes, you're actually going to learn why the Fourier trick is called the Fourier trick and, not the Giblin trick or whatever. But anyway, so the Fourier series is about reconstructing the entire time-dependent solution to a problem by breaking it down into the independent solutions of the differential equation, which in this case is the wave equation. So like we evaluate in the textbook, I'm going to walk through this for the case of a string where the string is going from 0 to L. Now, if you do this for some other domain, let's say you do it from minus L to L or 0 to 2L or whatever, you will get different transcendental functions. And that's something that you have to be aware of because there is no one Fourier series. There's a Fourier series for every combination of domain and boundary condition. And so this process of finding out what is the Fourier series going to look like is actually a pretty productive one. So if you understand it for the string going from 0 to L, what you should then do is practice it for the string going from minus L to L. At least this is going to be something that's going to be useful for you when you take quantum mechanics with me next semester. Anyway, so I'm gonna have this string going from 0 to L, and I'm gonna talk about it with Dirichlet boundary conditions. So really, the beginning of the string and the end of the string are both set fixed. So phi of 0 and phi of L are both set to equal 0, and that's true at any point. And so obviously, the solutions are each state is given by this function to. Oh, that's not obvious. Right. We've never done it before, right? This is the expression that we're going to get to, but why are these the solutions to this particular system, right? Why is this domain plus these boundary conditions going to give us this? So let's go through that quickly. This is something you should recognize from my previous video. When I start to try to come up with a quantization condition, or I try to start to come up with some idea for what the states look like, I always go back to what do solutions to the differential equation look like? And they look like this, where I have two different possibilities, right? Because the dispersion relation tells me that k is either plus or minus omega, right? So for a given omega, I have two different values of k, and they have an opposite sign. So if I take this and I evaluate it at 0, right? So phi of 0 then is going to be given, before I do anything, I set t equal to 0, right? Because I'm going to always talk about this in terms of an initial value problem, and so t is always going to be equal to 0. I can't believe I didn't do that. That would have been a disaster. Okay, now at phi of x equals 0, and let me make that explicit down here. So phi of x equals 0. Now we plug in x equals 0 to these two things, and I get that a plus b is equal to 0. This is kind of beautiful, because that means a equals minus b, or better, b equals minus a. I'm going to write it that way because unlike in the previous example where I never actually found the functions, I only found the quantization condition. Here I'm going to want to find the functions, and so I'm going to use this trick where phi is equal to, let's see, I can pull out the a, right, and I get an e to the I kx minus e to the minus I kx. Do you recognize that? Sure you do. That's a sine, right? This is sine kx times this is sine kx times 2i times 2i. Now, of course, I don't know what that a is yet, and so if if I don't know what a is, it doesn't really matter what 2I is. And so I'm going to say that this is equal to still some unknown constant a. Okay, I'll call it a prime, since it's really not the same a as before, times sine of kx. Right? Beautiful. And now that's kind of remarkable that one of the boundary conditions gives me this this definition for what the states are eventually going to look like. They're eventually going to look like sines. But if I do the other side now, and I do phi of x equals L, right, still evaluating it at t equals 0, I get that phi is 0 is a prime sine k L, right? Now, so if this is going to equal 0, when does sine KL equal 0? Well, sine equals 0, at pi, at 2 pi. So when KL is equal to n pi, there's my quantization condition. In other words, when k sub n is equal to n pi over L, then I have a solution, right? And that brings me back to how I'm going to look at these solutions phi sub. Now I'm going to call them phi sub n because they're indexed now by n, right? K can only take on certain values, and therefore I only have a certain set of functions that are going to satisfy this, and those are going to be proportional to sine n pi over Lx. Where, and we won't forget this, that k is actually n pi over L, right? That's how we get that weird n pi over L in that expression. And the question that you need to ask yourself now, well, I have these functions, right? Do those make up a good way of describing the system in general, right? Are they a good basis set of functions to try to describe any solution to this wave equation on the string? In order to answer that question, though, I have to have a philosophical moment with you where we discuss what it means for these functions to be states, right? It made sense when I was talking about a finite set of beads, right, and broke that into modes that were vectors. Those things really look like states, right? They look like eigenvalues. Here I have a function phi sub n, which is a function of space. Right? I have a lot of them. I have an infinite number of them, but they're indexed by a countable number n. So how does that go back to how we think about vectors? Well, each of these functions phi sub n of x represents what is a state that I'm going to write as a vector phi sub n. Okay. So when you're thinking about the function space that is defined by this physical situation, you have all of these different basis vectors. And now they're not vectors in real space like we think about them, right? Because I'm going to build up the function as a sum over these basis vectors. But each of these states then has an underlying function phi sub n of x, which is literally the function as a function of space. Right, and this is a subtle distinction, but it's one that we have to understand, and really textbooks do a pretty bad job at explaining. And maybe my textbook does a bad job at explaining it. But there's the concept of the state, which is the ket phi sub n, and then there's the actual function that corresponds to that state. And at some point, maybe you'll read the section on the nitty gritty of this, and you'll have an idea for what it means to actually have a function that's actually a state. Okay, and so when I try to decompose the full solution onto those states, if I look at it in vector form, which is this top expression, then I really see something that I recognize, where I have the full explanation is a sum over these states, right? It's a sum over the basis vectors for this entire solution, and the coefficient in front of those is the time dependent is a time dependent coefficient, right? How much is in that state, and then how much is it oscillating? If I want to write that as a function, all I have to do basically is drop the ket notation, where the function phi of x and t is a sum over the same coefficients times the basis functions. Okay. The thing that's missing, of course, is that how do you take products of these functions with each other? And so we need to define a new dot product, and maybe someday we'll calculate it. But for now, we're just going to take it as a definition. If I'm taking the bra-ket, right, the dot product of two states, well, what we used to do is multiply the first term and the second term and the third term. The Riemann sum version of that, of course, is just the integral of those two functions evaluated over the domain. And so if I find myself looking at this product, or the product of any two functions, as a bra and a ket, how I actually calculate that is I multiply the two functions together, and then I sum it over all of the different points along the string, which in this case, of course, my domain goes from 0 to L, but in principle, your domain could be something different from that. Okay, so now we at least have the language to talk about these different basis functions as a function space, right? Okay, so going back to my original question, is this a good basis? Well, we need to ask ourselves first, is this orthogonal? And then eventually we'll ask ourselves if this is normal. Okay, so to ask ourselves if it's orthogonal, of course, what we want to do is we want to find out if phi sub m dotted with phi sub n, is that equal to the, or something, is it proportional to the Kronecker delta, right? And I need to make it proportional, right? Okay, that orthogonality just means that the dot product of two different states is equal to 0. So if I actually plug this in for two different states, phi m and phi n, what I get is the integral from 0 to L of a sub m, a sub n, times sine n pi over Lx, times sine m pi over Lx. I probably should have written those in the other way, but whatever, it's no problem. So I end up with the integral of two sine functions times each other. And now it's actually important, it's really, really important that n and m are integers here. And so I think what you need to do, there's an explanation of how to do this integral analytically in the book. What I, of course, do every time I don't believe this, which happens every couple of weeks, is I plug different values of m and n into Mathematica, and it turns out that if you multiply any two sine functions over this domain, where n and m are integers, unless those two sine functions are exactly the same, this integral is actually 0. Which is kind of remarkable, right? And so this integral ends up being a sub m, a sub n, times delta mn, okay? And that delta mn really comes from the property of these transcendental functions as the properties of these transcendental functions and how you integrate them together, which is also kind of cool, okay? So they are orthogonal, right? If I have two different basis functions and I take their dot product, I actually get 0 most of the time, unless they're the same. So are we able to normalize it? Well, of course we are, right? And so actually I'm going to put a yes here, right? Yes, right? Is it normal? Well, I think it's possible to make it normal, because if I take phi sub n, phi sub n, right, I know that that's equal to am, an. I made a mistake here. This integral is not delta mn. It's delta mn times L over 2. Okay, so L over 2, right, times delta mn. And so if I want this to be just delta mn, right, then what I have to, so that is, if m is equal to n, this has to be 1. That means that all of my a sub n's must be the square root of 2 over L. Right? Because then I get the square root of 2 over L times the square root of 2 over L times L over 2, which is 1 times delta mn, and that solves all of my problems. Okay? And so these states have an additional factor of 2 over L, the square root of 2 over L, that allows them to be orthogonal and normalized. Okay? And that's how I construct these full solutions, where the function that defines my state, phi sub n, is the square root of 2 over L times these functions, where the sine comes from a boundary condition, the n pi over L comes from a boundary condition, and the 2 over L comes from requiring the states to be orthonormal. Okay, Feeling a little bit tired, but there's more to do, right? Because now I have these states. What do we do with them, right? Like, I spent all that time defining what the states were going to be like. What am I actually going to do when it comes to working with them? And so for this, I'm gonna give us a little bit of physical intuition for the problem that we might be able to look at, and that is, let's say that this is actually a string, right? A guitar string, and you pluck it, right? What you want to find out is, how is the guitar string going to move as a function of time? And so the strategy is much like we did for the blocks. We're going to take that initial condition, we're going to decompose it onto all of the different modes of the system, and then, since we know each of those modes has a different frequency, we can reconstruct the time-dependent system by doing explicitly that sum over modes. Okay, I'm going to do it here for some arbitrary function f of x. Okay, and so I'm going to call the function at t equals 0 for all x f of x, and that's going to be the initial condition. And for the purpose of this discussion, I'm going to say it's going to be at rest. All right, we'll get to that in a minute, but I just can't. I have too much emotional baggage today to deal with the string moving at its initial point. Okay. So I go down to my expression and I say that my full time dependent state, and I'm going to do the time domain in the complex parameterization for a moment, just because it reflects what we did in one of my last videos. So the full function is the real part of the sum over c sub n e to the I omega nt times the basis functions phi sub n. Okay, that's the thing I have to that's the thing that I have to do. So in order to actually do it, I'm going to employ the Fourier trick. Right? I want to be able to find out what those c sub n are. I need to find the real and the complex parts, right? And I know how to do this because I can take this expression and I can take the dot product, right, of this with some other basis function phi sub m. And so on the left-hand side, I get that phi sub m, phi of t, is equal to this basis vector. It doesn't care about the sum. It doesn't care about the real part. It goes right on through. Of course, I almost did it again. At t equals 0, right? Because at t equals 0, this is just going to be f of x, right? That's the initial condition. That's the state that's the place I'm going to use to define my modes. And so I now have the real part of the sum over n of c sub n, no e to the I omega t, times phi sub m, close this. Of course, there's an n missing there, right? And because we did such a bang-up job making these vectors orthonormal, this thing is just delta mn. The real thing can go right into the sum. The delta mn takes this sum and it says all of the terms are 0 except, of course, for the term when n equals m. And so this is going to end up being equal to the real part of c sub m, right? And nothing else, right? Because the delta function used up the sum and I'm left with just this. And that's going to be equal to phi sub m times f of x. Right, as a state. And of course, if I want to go one step further, the real part of c sub m, now, I can replace this dot product with the actual integral, right, 0 to L dx, of the square root of 2 over L times sine m pi over L x times f of x. Okay? And this looks bad, right? It looks hard, right? Especially because I don't know what f is. But it's doable, right? You've integrated before. You took Calc 2, right? You know what you're doing. And you can actually now calculate this and get some expression for what the c sub m's have to be. Now, I promised that I wouldn't do this, but I'm just going to show you the slide. If we did have derivatives, then I would play the same trick that I did for the finite system. I would take the derivative of both sides, set it equal to 0, apply the phi sub m, and you can now see that would give us some expression for the imaginary parts of the c sub m, but it doesn't matter, right? Because the initial velocities here are 0, and therefore every single one of the c sub m are 0. And so if I go back to so now I know how to calculate those c sub m's, right? I know how to calculate that set of coefficients. I'm going to plug it back into my original expression. So my full time-dependent state, right, my function of space and time, is going to be given as a sum over all of my states times the coefficients that we found, that family of coefficients C sub n, right? And we also found that in this particular case, those are real. So the real operator only hits the EDI omega t, which is of course just a cosine, times the states phi sub n. So I can expand that out a little bit, and I get the full answer to the Fourier series as we've developed it here, is that I can reconstruct the state as a sum over all of these n's, and then I can calculate the C sub m's. I can calculate the C sub m's like this. Okay. Now that is exhausting, but here are the steps, right? It looks hard, but it's really not so bad. Once you've defined the problem, the steps are always find out what the C sub m are given the initial conditions, right? What is that expression going to look like? What integral do you have to do? Then calculate those C sub m's, then reconstruct the entire state. Okay? Let's make this just a little bit easier by looking at it in Mathematica. Okay, so here's what it might look like in Mathematica. So I'm going to go through the steps that I told you that you had to do based on exactly the same notation that I had in the slides a moment ago. So I'm coming up with some really funky initial conditions. So it's one. So I'm going to let x go from 0 to 1 now. So I'm going to set L equals 1, just because in Mathematica I have to scale things to some level because I actually have to work with real numbers. Okay, so f is going to be given by this wacky expression, which looks like this. Okay, I can even make it worse. Maybe I will make it worse in a minute, but right now this is a pretty wacky initial condition, and again we're going to assume that it starts at 0. So the first step, the first thing that you want to do is to actually calculate the coefficients. So here I've identified terms, and I've set terms to 5, just so that I know how many terms I actually want to calculate, right? I'm not going to make Mathematica go to infinity. It wouldn't let me do that anyway. So what I'm going to do is I'm going to calculate my C's, those coefficients. The instruction in Mathematica to do things over integers is table. And so for each value of m from 1 to 5, I am going to integrate, and I'm going to numerically integrate, the square root of 2 over L times sine m pi x over L times the function f. Okay, and now Mathematica can do these 5 integrals really fast, right? And they're numbers, right? The bigger the number, the more of that mode. The smaller the number, the less of that mode, or whatever. But these are the first 5 terms. But those are just the coefficients of those terms. So to reconstruct the function, I have to take those coefficients, right? I have to take a sum over those coefficients times the basis functions, right? This is evaluated at t equals 0. And so I'm going to let n go from 1 to 5 terms. And then let's just plot it, right? Well, that looks nice, right? It kind of reminds me of the original shape. But of course, this is totally analytic. Look at this function. It's just 5 different signs with different weights. Now, where those weights come from almost look like magic, but it's just a sum of sign functions. And if I compare the output of the Fourier series to the original, it looks pretty good, right? I mean, the blue line, it overestimates a bit here, underestimates a bit there. But we knew it was going to be an approximation because, of course, I limited it to 5 terms. I have it set up so that I can do better. So this is the comparison with 5. Here's what happens if I go to 6. Here's what happens when I go to 7. Here's what happens when I go to 8. Here's what happens when I go to 10. Here's what happens when I go to 20, right? And suddenly, once I get to 20, you would ask yourself, well, do I really need to go any further? Those I don't seem to be adding much to the series after I've hit about, I don't know, 10 or 20 terms. Okay, great. But of course, the fun starts when I try to do the time-dependent state. So almost all of this is exactly what we did above. How many terms? Find out what the C's are. But now when I reconstruct the function, I'm going to keep that cosine n pi t in there, right? Omega is equal to k, right? And so if k is equal to n pi over L, omega is equal to n pi over L. So n pi over 1 times t. And that's going to give me a function of space and time. And so in order to produce something meaningful, I'm going to have to do an animation. So I'm going to plot this function over the time interval from 0 to 5, where each frame happens in 0.05 time units. And then I'm going to make all of my frames by plotting the solution, the time dependent solution from the Fourier series, and compare it to that original function, just so that we can keep things in our minds. So if I do that for five terms, it's going to take a minute, right? Because I'm making lots of plots. This is what the animation looks like, and I'm gonna not let Mathematica do it. I want to control it myself. So we start here, right? And it looks like a vibe. Oh, it's beautiful. I could watch this all day. Of course, then I wouldn't get anything done. I don't get anything done anyway. Anyway, look at that. Even sometimes it seems to return back to where it started. Of course, that's because I only have a certain number of terms, right? And so there's some common frequency that they all share. Oh, beautiful. Just for the sake of, because we can do it quickly, what happens if we do this for all 20 terms? Let's see how long it takes Mathematica to give this to me. Oh, not too bad, really. Okay, let's evaluate it. Come down here. Well, it actually looks pretty much the same, right? Those extra corrections due to the extra terms will add modes that are oscillating more faster, right? But they really don't change the way the solution looks at the end. Okay, I'm going to go ahead and upload. This Mathematica to the Moodle as well, so that if you wanna try along with the video, you'll be welcome to do that. All right, good luck, and I hope you too get some sleep.